Have you ever stopped to think about how the same basic rules of chemistry can be used to solve problems at completely opposite ends of the scale? I mean, we're talking about going from the immediate, desperate survival of one single person all the way to the long-term survival of the entire planet. It's an incredible journey, really, from a single breath to our global atmosphere. And it all kicks off with a simple little box that literally makes air out of thin air. Okay, so picture this. You're trapped. You're cut off. The air around you is totally unbreathable. Your entire life, right now, depends on this small device that's chemically creating fresh oxygen from your own breath. I know, it sounds like something straight out of a sci-fi movie, but this is 100% real. And the chemistry that makes it work is, well, it's just incredible. So let's dive into this little personal survival gadget. It's a piece of tech that pulls off a trick that must feel like actual magic when your life is on the line. It's officially called a self-contained self-rescuer, or SCSR for short, and it's built for the absolute worst case scenarios, like a miner trying to escape a fire deep underground. Now, this isn't just a tiny scuba tank full of compressed air. No, this is a miniature chemical factory that you wear, and it literally generates oxygen for you to breathe on the spot. But here's the twist, and it's a big one. The very same chemistry that's working to save your life is also incredibly powerful. And if something goes wrong, it's extremely dangerous. All right, the star of the show inside this box is a chemical called potassium superoxide. Here's how it works. You breathe into the device, and the moisture and the carbon dioxide from your own breath react with this chemical. The result? Life-saving oxygen. But it also creates a nasty byproduct, potassium hydroxide, which is a seriously corrosive and alkaline substance. And that's not the only thing to worry about. The safety warnings are intense. The potassium superoxide is a strong oxidizer, which means it loves to make things burn. Another ingredient, lithium hydroxide, is a corrosive solid. So yeah, this box is an absolute lifesaver, but if it gets damaged, you've got a whole new set of problems on your hands. And this is where the chemistry just gets weird and completely counterintuitive. There is a massive critical warning on this thing. If it ever catches fire, what's your first instinct? Douse it with water, right? Well, that would be a catastrophic mistake. Throwing water on it would actually cause a reaction that generates more oxygen, which would be like pouring gasoline on the fire. The first aid instructions really drive home just how dangerous this stuff is. We're talking flushing with water for 15 minutes straight, getting to fresh air immediately, and in every single case, getting medical attention. This is powerful, volatile chemistry designed for only the most extreme situations. Okay, so we've got this incredible, if a little scary, chemistry that can fix the atmosphere for one person in a pinch. But that got me thinking, what if we could take that same core idea, chemically changing a hostile atmosphere, and scale it up, like not just for one person, but for the entire planet? You know, the two problems are almost perfect mirror images of each other, right? For the miner, the problem is not enough oxygen. For our planet, it's way too much carbon dioxide. So if a chemical reaction can solve the first problem, could a different kind of chemical reaction solve the second? Now, let's be clear, this new challenge is way harder. We need to take really stable CO2 molecules right out of the air and, using only light for energy, turn them into something useful. Something like carbon monoxide, which can be a building block for synthetic fuels. This whole process, using light to kickstart a chemical reaction, has a name: photocatalysis. Photo for light, catalysis for speeding up a reaction. And the key to making this all work might just be found in a bizarre, kind of wonderful new type of material. And its secret weapon is something we usually try to avoid at all costs: being imperfect. They're called high-entropy oxides, or HEOs. And the best way to think of them is as a kind of chemical cocktail. Instead of one or two main ingredients, you've got 5 or more different metals all jumbled together in a single crystal. And all that chemical chaos, well, it gives these things some truly extraordinary properties. So the more elements you add, the more random and disordered the inside of the material becomes. Scientists call this configurational entropy. And here's the really wild part. This high level of messiness actually makes the final material incredibly stable. This disc right here was made under huge amounts of heat and pressure, and it's rock solid because of that principle. So this is the thing you really have to wrap your head around. For these materials, the flaws aren't a bug, they're a feature. Their incredible power comes directly from their imperfection. Let's break that down. First, you've got the cocktail effect from all those different elements. Now, because all those atoms are different sizes, they don't fit together neatly. It creates these built-in defects and puts the whole crystal structure under a ton of strain. And it's that combination, the disorder and the stress, that creates these perfect little hotspots for chemical reactions to kick off. And this isn't just some idea on a whiteboard. When you look at this stuff under a seriously powerful microscope, you can literally see the distortion. The rows of atoms aren't in nice, neat lines. They're warped and strained. And those tiny, nanoscale imperfections, that's exactly where the CO2 conversion magic happens. Okay, so the theory is fantastic. The material is stable, and its defects should make it an amazing catalyst. But, you know, talk is cheap. How does it actually perform when you put it to the test? So here's the setup. Researchers ground the HEO into a powder, mixed it in water inside this photoreactor, and then started bubbling CO2 through it, all while blasting it with a powerful lamp to act like sunlight. The simple goal was to see if it would actually convert any of that CO2. And the results? Well, they're pretty incredible. In this direct comparison, the new HEO material, that's the blue line, produced carbon monoxide at a rate that's almost identical to the purple line. And that purple line, that's P25 titanium dioxide, which has been the industry's gold standard for years. And it just blows these other common catalysts out of the water. The hard numbers confirm exactly what we just saw. The HEO came in at 4.64. The industry benchmark, P25, came in at 4.63. I mean, that is a statistical tie. This brand new, supposedly defective material is performing right up there with the absolute best in the business. But wait, because that's not even the most amazing part of the story. Here's the real kicker. The HEO achieved this top-tier performance despite having a surface area that is 60 times smaller than the benchmark. 60! This means it's fantastically more efficient, site for site. Its imperfect surface is just that good at doing its job. Which brings us right back to where we started, doesn't it? From a desperate, life-saving chemical reaction in a miner's rescue pack to this elegant, light-driven conversion in a futuristic fantastic catalyst that works because of its flaws. We've pretty much figured out the chemistry to survive a disaster after it happens. The real question is, can we master this new, imperfect chemistry to prevent one from happening in the first place?